Okay, we're on to chapter 15, problem set, dealing with chemical equilibrium. So let's look at this equation here. Carbon monoxide plus two hydrogens in equilibrium with methanol. What is the equilibrium expression? So equilibrium expression is the products over the reactants raised to their stoichiometric coefficients. So it's the concentration of methanol divided by the concentration of carbon monoxide times the concentration of hydrogen squared. So the two there is from the two hydrogens in the reactant side of the chemical equations. And those brackets, that means concentration in moles per liter. So if you wonder what the brackets mean, that means moles per liter. So write the equilibrium expression for this reaction, decomposition of calcium carbonate to lime and carbon dioxide. So calcium carbonate in equilibrium with calcium oxide and carbon dioxide. So you think right away, oh, we just did the equilibrium expression. It's the products over the reactants. So concentration of calcium oxide times the concentration of carbon dioxide divided by the concentration of calcium carbonate. Now, the problem is calcium oxide and calcium carbonates are solids. Their concentration doesn't change. Therefore, their values are absorbed into the equilibrium constant. And then the equilibrium constant is just the concentration of carbon dioxide. So do not include solids or liquids in equilibrium constants when you write them. So please keep that in mind. So let's calculate some equilibrium constants. 2 methanes in equilibrium with acetylene and 3 hydrogens. So we have a mixture at a specific temperature, equilibrium concentration. Our methane is 0.0203 molar, acetylene 0.0451 molar, and hydrogen 0.112 molar. What's the value of the equilibrium constant in this temperature? So we write out the equilibrium constant, and its products over the reactants raise their coefficients. So equilibrium constant is acetylene times hydrogen cubed divided by concentration of methane squared. We're given the we're given the equilibrium concentrations. We put those values in and we calculate the equilibrium constant then to be 0.154. And we're done with that one. So let's look at this reaction. Hydrogen plus iodine in equilibrium with 2 hydrogen iodides. The equilibrium constant is 69 at the specific temperature. We find that the concentrations in equilibrium of hydrogen and iodine are both 0.2 molar. What is the equilibrium concentration of hydrogen iodide? So again, we're going to have one equation, one unknown. We're given the equilibrium constant, but we're not given the equation. So you can write out the equation. The equilibrium equation is products over reactants raise their coefficients. So hydrogen iodide products, so Hi squared, because it's 2 hydrogen iodides over the reactants hydrogen and iodine. So we can solve for the concentration of hydrogen iodide. And then furthermore, we can take the square root to form it just to be concentration of hydrogen iodide. And then we plug in the numbers. So the equilibrium constant is 69, and the initial, well, I should say, the concentrations, the equilibrium for hydrogen iodine are both 0.2. And then we get 0.17 molar. So I'm wondering, someone's going to say, wait a second, square root is plus and minus. So what happened to the negative 0.17 molar? So the fundamental theorem of algebra states the polynomial of x raised to the n power has n roots. What does that mean? That means that whenever you have a polynomial raised to some power, the number of roots, the number of time it crosses the x-axis or 0 equals the number of whatever the order of the polynomial is. So when you square something mathematically, you create a second root. So the thing is, math is not real. Math is a model. It's a very, very good model. It's a very useful model, but it's not real. We use it as a model. And chemistry is an observational science. It is real. We are dealing with real data. And with that, and with the math, when you square something, you create the second root, but only one of the roots makes sense. So although math is a very powerful model, you as the scientist have to interpret the results of the mathematics to find the root that makes sense. So negative concentrations do not make sense. That is not what antimatter is either. You're not looking at antimatter. Only the positive root makes sense. with this. Also, for these, we don't have, although we can use complex numbers, we do not have complex or imaginary numbers as solutions. So only positive, real numbers are able to be used with this. So keep that in mind for the math whizzes there that wonder where the negative root went. So we can also check this. So if you want, you can plug it back in the equilibrium expression to see if you get the value coming out. And originally it was 69, now we're getting 72. But this is close enough. If you're wondering, like if you got something like 1,000 or something like that, then you knew you did it wrong. But 72 is close to 69. And the general rule of use this is if it's within 5%, then you're okay. You're like, wait a second, well, how do I know? It's if you're kind of within 5%, that's a good show that you're about right. And with this though, so where did the error come from? I mean, from here it's written as a rounding error. I would call it a truncation error. So could you truncate out those numbers? And truncate means you chop off the extra numbers. So if you're using your calculator, you can see there's a bunch of numbers there, and you can, well, how far you want to go. But the thing that we're dealing with real measurable science is that we have significant figures, and with the significant figures and also the measurement, we have error associated with that. So that's one thing about dealing with chemistry, and then the math associated with chemistry is that you have to manage your error. And this is just part of the error that would be indicated within normal measurements and whatnot. So that is why it's not exact. If you're wondering, and actually this concept, it does bother students quite a bit. If you feel bothered by this, then you are not alone. But it has to do with the fact that when you have a measurable science based off of data, there's error, and you have to manage that error. And you have to manage the error with the measurements. You have to manage error in the models, and that kind of thing. We already talked about how math is not a perfect model, right? Because you're creating false roots with the same problem. So lots to learn in this problem, right? So let's talk about Le Chatelier's principle. Le Chatelier's principle deals with how the stresses on the system and how the system at equilibrium responds to it. So we have calcium carbonate in equilibrium with calcium oxide and carbon dioxide. What's the effect of adding more carbon dioxide to the reaction mixture? Well, if you look at the equilibrium constant, it's just carbon dioxide, right? Because the solids are not included. So if you increase the pressure of carbon dioxide, it was the same thing as increasing the concentration. You shift left. You shift left towards the reactants. So left is to the reactants, right's to the products. And then if you add calcium carbonate, the thing is calcium carbonate is a solid. You don't increase. It doesn't do anything. Like it's because the concentration is constant. You're not changing the concentration. Therefore, it doesn't affect the equilibrium. So the solid calcium carbonate does not affect the equilibrium. So let's look at this for volume. Same thing. So decreasing the volume, the same thing as increasing the pressure. So what is the effect of decreasing the volume? So decreasing the volume is increasing the pressure, and you shift left towards the side that has fewer moles of gas. So and the same thing with increasing the volume. It's the side that has more moles of gas. You shift that way, and so you shift right for increasing the volume. So that's the system is responding to the stress by trying to counteract that stress from that. So let's look at temperature. So calcium carbonate and equilibrium calcium oxide and carbon dioxide. So this is an endothermic reaction. You need to have heat to make this go. So what is the effect of increasing the temperature? So since it's endothermic, increasing the temperature means you shift right. It's the same thing as adding more reactants. So adding more reactants is going to shift right towards the product. And let's talk about the solubility product constant, the KSP. What is a KSP for each of these? So barium sulfate, manganese 2 hydroxide, and silver chromate. So first of all here, barium sulfate in equilibrium with barium ions plus sulfate ions. So then the Solubility of product constant, so same thing, products over reactants. The thing is the reactant is solid, it's not included in the equilibrium expression. So we have the barium plus 2 ions times the sulfate anions, and just leave it at that. For manganese 2 hydroxide, we have manganese plus 2 ions and 2 hydroxides in the equilibrium expression. Therefore, it's going to be the concentration of manganese plus 2 times the concentration of hydroxide squared. Now for silver chromate, similarly, we're going to have the silver squared because there's 2 of them, and then the chromate as the second one. So now we're going to calculate the molar solubility of barium sulfate. And so we've written out the KSP. We did that in the previous problem as well. So the molar solubility S, we're going to call it S. And then this, because it's all 1-to-1 there, so every mole of barium sulfate is going to be a mole of barium, mole of sulfate. And so the KSP is S squared. So then the molar solubility is the square root of the KSP. And we look at the KSP and you plug it in and you get 1.03 times 10 to the minus 5 molar. And so with this, the salts here, they're sparingly soluble. So this is for a sparingly soluble salt. So you look at something like, for instance, like sodium chloride. Sodium chloride is about, it's a 1-to-3, one part mass sodium chloride to 3 parts mass of water. That's about the solubility of sodium chloride. And that's a lot. If you ever try to make a brine solution, you're going to be dumping lots of salt in that water. So whenever I make brine, I'm like, man, this is taking forever. I can't believe I have to use this much salt to make a brine solution. So with that in mind, right? So if you have a liter of brine solution, there's about 250-ish grams. I don't know what the exact number is, but it's going to be about 250 grams of sodium chloride in a liter of brine. That's a pretty sizable amount of sodium chloride, right? 250 grams. That's like a half a pound for you American folks. I'm American too, I know, but I'm using colloquial terms. That's a lot of salts, right? Half a pound of salt in a liter solution. That's a lot of salt. Now you look at so 10 to the minus 5 molar. So looking at that's 0.00001. So 4 zeros in front of that 1. That's not a lot of stuff. That's a very sparingly soluble. So when you use these equilibrium expressions for very sparingly soluble, that's very, very small. So keep that in mind with that. And we are at the end of this. Thank you for listening.